Hello, our viewers. Here I come again in grade 12 magnetism concepts. Previously on our topic, we have tried to see about how to determine the magnetic force on a straight current carrying conductor. At last, we have tried to find the force using vector notation form, and we have also tried to determine the magnitude. So whenever a straight current carrying conductor is immersed into a uniform magnetic field, it's possible to determine the force, the magnetic force exerted on this wire as F equals to I current, length L, cross magnetic field B. This is how we determine the magnetic force exerted on a straight current carrying conductor immersed into a uniform magnetic field. As you see here, there is a straight current carrying conductor and it is immersed into a uniform magnetic field which is acting into the page. Then it's possible to determine the magnitude of the force as BIL sine theta, where theta is the angle between the, it's possible to say, the electric current I and the magnetic field B. It's possible to find the force, and it's possible again to use right-hand rule to determine the direction of the magnetic force exerted on this straight current carrying conductor. Previously, point charged particle, moving charged particle, is possible to determine the magnetic force as QV cross magnetic field B. This is a way how to determine the force exerted on a point charged particle. Like that, it's also possible to determine the magnetic force exerted on a straight current carrying conductor. So this was the point at last that we have seen previously on our discussion. So today we'll proceed on that. And at last I have gave you this problem to find the magnetic force exerted on these wires. For example, in the case of A, there is a magnetic field which is acting upward, and the wire is found or oriented like this, is kept like this, which is perpendicular to the magnetic field, What is the magnetic force on a wire of length 6 centimeter carries a current of 10 milliampere A to B, meaning if the current is directing from A to B, in each case, if this is the direction of the electric current, and if this is the direction of electric current from A to B, so in a uniform magnetic field of 12 millitesla oriented as shown. So in the case of A, the current carrying conductor is perpendicular to the magnetic field. In the case of C, it's parallel to the magnetic field. But in the case of B, it's found at some angle, theta, which is 30 degree. Therefore, it's possible to determine for each case, the magnetic force exerted on each case. So what are the given parameters or the given variables? Well, the given variables are the length and the current as well as the magnetic field. The length is given to be, so the given variables, length is given to be 6 centimeter, so 6 times 10 to the power of minus 2 meter. The other variables are 10 milliampere, the current is given to be 10 milliampere. Milli means 10 to the power of minus 3 ampere. And there is a magnetic field which is acting vertically upward, which is 12 millitesla. This is what the given variables are. Therefore, at last we are asked to find the force. Therefore, the force for case A, to determine the force, BIL sine theta. This should be the way how to determine the magnitude of the force for a current carrying conductor immersed in a uniform magnetic field. Therefore, in this case, it's possible to have 12 milli means 10 to the power of minus 3. Then it's possible to have the current 10 milli again, minus 3. Here millitesla, this one is milliampere, and the length is 6 centimeter, 6 times 10 to the power of minus 2 meter. And sine what? Sine 90. In this case, the current, let's back again. Look it here. So the current is acting from A to B. Look at here. The current is acting in this direction, and the magnetic field is acting upward. So the angle between them is 90 degrees. So it's possible to have the magnetic field is acting vertically upward. The current is acting in this direction. The angle is 90 degrees. Therefore, it's possible to determine the magnetic force to be 7.2 times 10 to the power of minus 6 Newton. It's possible to find the force exerted on this wire as it is oriented perpendicular to the magnetic field. And the other concept here is it's possible to determine the magnetic force exerted on this wire. It's possible to find the magnetic force here. But the magnetic force in the case of C, the force is BIL sine theta. What is theta? Theta is the angle between the magnetic field B is acting upward as well as the current is acting upward. Both are acting along the same direction. Theta is 0. So sine 0 gives us 0. So the force exerted is 0. Okay? But here we have sine 30 degrees and it gives us half of 7.2 here. We have already determined the maximum force, and sine 30 is half. Therefore, it's possible to have half of the magnetic force. Okay? Therefore, to find the answer, here we have the answer, 7.2 micronewton, 3.6 micronewton, and at last, 0. Now, let's proceed. Let's try to see about the torque exerted on a current-carrying loop. Okay? So, torque on a current-carrying loop. Let's try to determine the net force exerted on a current-carrying loop. So far, we have tried to see about the force exerted on a point charge particle. Then we have tried to see enormous amount of point charge particles passing through a length L. Okay? It's possible to find the force on current carrying conductor. It's possible to find magnetic force on a point charged particle. And now what if this current carrying conductor is oriented as loop like this? If you have a loop, what will be the force exerted on this loop? We call it to be torque. We call it to be torque because that's the net force tends to rotate this loop, and we'll try to determine this concept. Here we have, consider a rectangular loop and carrying a current of I, and it is placed in a uniform magnetic field as shown here. Let's take this to be the loop, rectangular loop, and you have a magnetic field which is acting to the right in this direction. Therefore, it's possible to have, for example, here you have the current I on segment 1. There are segments here. Let's say that this is point A. You can call it to be B, C, D, and so on. Therefore, from A to B, from B to C, D, and so on. Therefore, the length from A to B, you can call it width or W. Let's call it to be W. Or it's possible to call this one from B to C as L. So in this case, as we have seen previously, the magnetic field and the current are acting oppositely. When they are acting oppositely, the angle is 180 degrees. 180 degrees. Let's see here. If this is the rectangular loop, the current is acting in this direction, whereas the magnetic field are acting in this direction, to the right. So the angle theta is 180 degrees in the case of the first segment. Then the current comes here and it moves downward. Since the current is acting downward, the magnetic field is acting to the right. They are perpendicular to one another. Then the current comes here and tends to move in this direction. So the current is acting to the right, as well as the magnetic field is acting to the right in the case of the third segment. And the fourth segment, the current is moving upward, whereas the magnetic field is acting to the right. So they are perpendicular. So let's see this one. In this case, the current and the magnetic field are opposite. In this case, the current is moving downward, but the magnetic field are acting in this direction. They are perpendicular to one another. And in this case, the current comes here and moves to this direction in the third segment. So the current is acting in this direction. The magnetic field is as well acting in the same direction. So in this case, theta is 0, since they are acting along the same direction. In this case, since they are acting oppositely, theta is 180 degree. Well, theta is the angle between the electric current and the magnetic field. We have already mentioned that. And in this case, the current is acting downward, whereas the magnetic field is acting in this direction, so it's 90 degree. At last, on the fourth segment, the current is acting upward, the magnetic field is acting in this direction, so the angle theta is 90 degree, 90 degree. Therefore, the force exerted here and here are maximum, whereas the force exerted on these segments are zero. Therefore, it's possible to find the force exerted on this segment and on this segment only. Therefore, the force exerted on this segment, since it carries a length of L, or it's possible to say A, okay? You can call it L, and this one you can call it W as well. It's possible to call it W or B. To find the area, length times width. It's possible to use length and width. So, the force exerted here, it's possible to use right-hand rule to determine the force exerted on this segment. The magnetic field is acting in this direction, the current is acting downward. So, using right-hand rule, it's possible to determine the magnetic force exerted on this segment. The magnetic field is acting to the right, the current is acting downward. So, using your right-hand rule, your thumb points towards you, meaning this segment is moving, tends to move towards you. So the force exerted here is out of the page, and out of the page can be represented using dot. So the force exerted on this segment is out of the page. Let's see, in this case, the current is acting upward, as we have already mentioned previously. The magnetic field is acting to the right. So using your right-hand rule, the current is acting upward, the magnetic field is acting towards the right. So your thumb points to the direction in which the force is acting towards or into the page, like this. Meaning this segment tends to move into the page, whereas this one is tending to move out of the page. So there is a turning effect, rotational effect. Such an effect of force is known as torque. So the torque from couple force system, is possible to determine the torque like this. We know that in couple system, force F times D, where D is the distance between the two forces. For example, let's take this segment. There is a force which is acting in this direction. There might be a force which is acting oppositely to the other direction. And the distance here is D. Here we have force, equal force in magnitude. They are equal in magnitude and acting oppositely. They tend to rotate objects. Therefore, F times D. It's possible to find F times D, where D is the distance between the two forces. In this case, in our case, previously, the distance from this to this is B, or you can call it to be W. We can call it to be width. Okay? So the force exerted on each segment is B-I-L. It's possible to say L, okay? B-I-L. Again, the force exerted on this segment is B-I-L. Therefore, taking the force and the distance is possible to determine the torque or the moment of force. Therefore, the torque tau is force times D. The force F is B-I-L, and the distance D is termed as width. Therefore, length times width is known to be area. So the net torque exerted on a current carrying loop can be determined using this equation. And we have a new term, which is the product of electric current I and area is known to be magnetic dipole moment, or it's known to be magnetic dipole, and symbolized as mu. You can see here, it's possible to determine current I be sine theta, but the product of currents and area is known to be magnetic dipole moment, and it's symbolized by a Greek letter mu. And it's a vector quantity, and its direction is along the area. Actually, when we say area has no direction, rather the normal line to the area. If you have such area, there is a line, perpendicular line. This is known to be the direction which determines the direction of the area. The normal line is the one which determines the direction of the area. Therefore, the magnetic dipole is acting along the normal line to the area, the normal line to the area. So this is how we determine the net torque exerted if you have n number of loops. In this case, we just have a single loop, but you might have a number of loops, okay? A number of loops like this. You can have number of loops wound. Therefore, it's possible to use n. N means if you have n number of turns or n number of loops. And current times A is already mentioned above. It's known to be magnetic dipole moment. So we have a very important equation. Very important equation. So students, can you try to solve this problem? Please try that. Students, I hope you have tried to answer this one. Actually, the question has two parts. The first question is to determine or to calculate the magnitude of magnetic dipole moment. Magnetic dipole moment. Here we have a rectangular loop of 5.4 by 8.5, and it consists of like 25 turns. Okay, there is an n number of turns, and that is 25, and it carries 15 milliampere current. So it's possible to calculate the magnetic dipole moment. Already you have the equation, mathematical expression as I times A. You can find area by multiplying the length and the width as well. And it's also possible to determine the magnitude of the torque from the equation that we have previously provided or found. So your answer is this one. I think you have already determined the magnetic dipole moment is 6.9 times 10 to the power of minus 5, and the unit of magnetic dipole moment is ampere meter squared. Since it is magnetic dipole moment means I times A, the unit of electric current is ampere, the unit of area is meter squared. And it's also possible to determine the torque tau, tau as mu n times mu naught times magnetic field B times sine theta. It's possible to find this. For a maximum torque, theta should be 90, and the angle between the magnetic dipole moment and the magnetic field. N is number of turns. It's already given to be 25, so your answer should be 6.04 times 10 to the power of minus 4 Newton meter. I hope you have tried to determine this. Now let's proceed. So far we have tried to see what if point charge particle is immersed in magnetic field. What if a current carrying conductor is immersed into a uniform magnetic field? What if rectangular loop or any other loop is immersed into a uniform magnetic field? Now we have a very interesting question or a very interesting subtopic. Is it possible to determine magnetic field around a current carrying conductor? This was one of the famous questions in the early 80s and 90s. So a Danish physicist known to be Hans Ørsted is the first physicist who determined that it's possible to determine magnetic field around any current carrying conductor. In his famous experiment, he uses a compass. Actually, compass deflects whenever there is a magnetic field brought nearer to it. So Hans Ørsted brought the compass nearer to a current carrying conductor. I hope you have learned this in lower grade. Therefore, let's see this one. Here we have a current carrying conductor, and it carries a current of I. When you brought a compass, when Hans Ørsted brought a compass nearer to this, when there is a flow of electric currents through this, the compass deflects. When current is switched off, the compass does not deflect. It aligns its original north-south position. So Hans Ørsted had found this interesting phenomena. It's possible to determine magnetic field B using not a magnet, rather using a current carrying conductor. Produce a magnetic field, you don't need a magnet necessarily. Rather, it's possible to use a current carrying conductor to produce magnetic field. So Hans Ørsted had found this first relation, the relation between magnetism and electricity. It's possible to determine magnetic field B using what? Using flow of electric current. This is electricity and this is magnetism. So after that, other scientists start to ask the reversed question. We'll try to see this in the next unit, electromagnetic induction. So if it is possible to produce magnetic field B, how do we determine the magnitude? How do we determine the direction? So it's possible to determine the direction and the magnitude. First, in his experiment, Hans Oersted found that the magnetic field B has a direct correlation with the magnitude of the current I. As the current increases, the magnetic field strength also increases. The other point is, it has a linear inverse relation to that of the distance separation from the current carrying conductor. As you go further from a current carrying conductor, the magnetic field gradually decreases linearly. So therefore, equating these two equations, the first equation or the first experimental evidence shows that magnetic field has a direct correlation with current carrying I. And magnetic field has inverse relation with the separation distance r. Therefore, equating these two equations and introducing a constant k, it's possible to find a magnetic field around any straight current carrying conductor as mu naught, permeability of free space, current I over 2 pi r, directly proportional to the current and inversely proportional to the distance from the separation. So this is a very important equation in this unit in magnetism. Now, how do we determine the direction? We have already determined the magnitude. How do we determine the direction of the magnetic field? So to determine the direction of the magnetic field, we have so many right-hand rules. Among that, one is you have to point your thumb to the direction of electric current and try to grasp or catch the current carrying conductor. So point your thumb to the direction of the electric current. If the current is moving upward, point it towards upward. Then when you grasp it, you have a concentric circle like this. So the direction of the magnetic field at this point is like concentric circle. So if we take straight current carrying conductor, and that straight current carrying conductor carries a current I. So as it carries a current I, you are pointing in this direction, your thumb points upward and your forefingers points in this direction. So it's moving like this, in this direction. Therefore, from the right side of the straight current carrying conductor, there is a magnetic field which is acting into the page. We can call it like this, into the page. You are pointing into, your forefingers points towards into. So it's pointing, then turning. Since it is concentric circle, it is in, then out. In this direction, it's moving out. Okay? So the magnetic field to the left side of the current carrying conductor is out. So in this case, it points us out of the page to the left side. To the right side, it's into the page. So into, out. So this is how we determine the direction of the magnetic field around a straight current carrying conductor. So we have seen two things. Previously, we have tried to see how to determine the magnitude of a magnetic field around a straight current carrying conductor at any distance r. The second case is, it's possible to determine the direction of the magnetic field around a straight current carrying conductor. So this was that we see. And let's proceed again. Here I do have a single exercise. Try to determine the magnetic field at a distance of 2 millimeters from a straight current carrying conductor which carries a current of 5 ampere downward. It carries a current of 5 ampere downward, and we are asked to find a magnetic field at a distance of 2 millimeters to the right side of this wire. So please try to find this. Well, to determine the answer, already you have the radius r, or the distance r, and here you have the current I. We are asked to find the magnetic field at a distance of 2 millimeters to the right side of the current carrying conductor. So the given parameters or the given variables are, first r, the distance r is 2 millimeters, which means 2 times milli means 10 to the power of -3 meter. and the other is current is given to be 5 ampere, which is acting downward. So we are asked to find the magnetic field B. The magnetic field from the amperes from the previous equation, magnetic field B is equals to mu naught permeability of free space I over 2 pi r. This is how we determine the magnetic field. And permeability of free space is already known, and on our previous discussion I have already mentioned it. It is 4 pi times 10 to the power of minus 7 Tesla meter per ampere. This is how we determine the permeability of free space. Therefore, you have to substitute all the variables here and try to determine magnetic field. Mu naught is 4 pi times 10 to the power of minus 7. Current is 5 ampere. And here you have the distance 2 pi. And the distance r is 2 times 10 to the power of minus 3. So when you calculate this one, you'll have a result of 5 times 10 to the power of minus 5 Tesla. 10 to the power of minus 5 Tesla. By the way, there is also a non-SI unit known to be Gauss. Previously, I have mentioned that 1 Gauss is equivalent to that of 10 to the power of minus 4 Tesla. So you can equivalently resubstitute it as 5 times 10 to the power of minus 1 times 10 to the power of minus 4 Tesla. Okay? 5 times 10 to the power of minus 1 gives us 0.5. 0.5 times this one can be substituted as Gauss. So the magnetic field can also be given as 0.5 Gauss in honor of Carl Friedrich Gauss. Here we have the magnetic force between two parallel current carrying conductors. So far we have tried to see the magnetic field around a straight current carrying conductor. And again, we have, let's take two parallel current carrying conductors. On these two parallel current carrying conductor, there will be a magnetic interaction between these two wires. If this wire carries a current of I and I1, and the other wire carries a current of I2, there will be interactive force, and that interactive force is magnetic force between the two parallel current carrying conductors. Two arrangements. The first thing is both wires may consist the same current upward, or they may consist oppositely. So these two wires carries a current of I1 and I2. These two wires carries a current of I1 and I2 but opposite in direction. Therefore, this wire, since it carries a current of I1, it can produce a magnetic field around it, to the right side and to the left side. So it can produce a magnetic field which is into the page to the right side. And to the left side, it produces a magnetic field which is acting out of the page. The same is true for these two wires. Then it's possible to find the magnetic field is weaker in between the two wires, because the left side of the magnetic field produced by current I2 is out of the page. The right side of wire 1, the magnetic field produced by the wire is into the page. And this one is out of the page, into the page, and out of the page are cancelling one another. So we have a weaker magnetic field in between these two. If we take a straight current carrying conductor, which carries opposite current, the current I1 produces magnetic field to the right side into the page, but to the left side out of the page. This one, since it carries a current of I1 downward, in this case, let's take this here. Since it carries a current downward, to the right side and to the left side is changed. To the left side is into the page. To the right side is out of the page. So when you rearrange these two, there is a magnetic field which is acting to the right side of wire 1 into the page, to the left side of this wire 1 as well into the page. So in this case, the magnetic force are reinforcing one another. The field lines, both the field lines are acting into the page due to current carrying conductor 1 into the page, due to current carrying conductor the page. Therefore, there is a strong magnetic force between the two wires when they carry opposite current direction. and there is a weak magnetic force in between the two current carrying conductors which carries the same current direction. So how do we determine the interactive force between the two wires? The interactive force between the two wires can be given using this equation. Actually, it's possible to determine using previously, if a current carrying conductor is immersed into a uniform magnetic field, it's possible to determine the force. For example, this wire is found in a magnetic field. In a magnetic field which is produced by wire 2. The first wire is found in a magnetic field produced by wire 2. The second wire is found in a uniform magnetic field produced by wire 1. So it's possible to determine the force exerted on wire 1 due to the magnetic field produced by wire 2. This wire 2 carries a current I2 and it can produce magnetic field all around it. Therefore, it is always under the influence of the second magnetic field. Therefore, the equation is the general equation. Let's see this one. The general equation can be determined as the force per length is equals to mu naught I1 I2 over 2 pi r, where r is the distance between the two current carrying conductors, parallel current carrying conductors. When two parallel current carrying conductors have the same current direction, they have attractive force. When they have the same current direction force, they have an attractive force. But when they are opposites, the same current direction, like this, they have attractive force. When they are opposite to one another, they have a repulsive force. Don't forget this one. When they have the same current direction, attractive force. When they have opposite current direction, repulsive force. When they have the same current direction, they have a weaker force in between. Students, finally, these points we have to finalize. The force between two current carrying conductors acting along the same direction is stronger. In between the two current carrying conductors which carries the same direction is weaker. The force in between is weaker, whereas when they are oppositely acting, they have strong force. Therefore, we'll try to see about Ampere's law and Biot-Savart's law next time. So see you then.